Okay, after completing the instrumentation related to CT, now we are all set to move on to the image formation. I would recommend this and probably the next lecture together. This material that we are going to cover could turn out to be one of those, really important yet very interesting, right? In fact, I after going through this and didn't really have a formal orientation to this course until I really started working in the field, right? So when after your basic engineering, irrespective of whichever program you go through, right, this is something that is like so interesting and so powerful, yet we are not really introduced to this topic. Okay, we all are introduced to Fourier transform, thankfully, right, irrespective of whether you are from electrical or mechanical or civil or whoever, right? But unfortunately, the material that we are going to cover is so powerful, right, and so interesting and so much used in so many different fields, but somehow it doesn't get the attention it needs. So the way I would like to cover this is in a way where it is like very common sense approach. However, it has a rich pedigree, and the mathematical complexities are really something that is kind of unnoticed. Okay, so with that, I would request you to really go over this part, go through these lectures, and go after this, go do the homeworks, right? Go through the assignments, go self-learning, go read about it, and you will find whatever we are going to cover in this slide, in this module and the next one. So about a couple of hours worth of this material. I think that's a eye opener. At least I felt it as an eye opener. I hope you do so. Okay. Without much more wait, let's get on to the image formation. So what do we know already, right? It's always going to be what do we know already, what we have done, because the physics and the model we have established already. Because projection radiography, we already talked about X-ray interaction, and we talked about what is signal and what is noise, right? So what we know already is, here in CT, like in projection radiography, you are going to send X-rays, but only thing is it is going to be sent. In projection radiography, we sent a cone, so the whole chest was insonified, right? But sorry, irradiated. But then when you take CT, we are going to in the end come up with slice, so through the depth, right? So we are going to now send CT like this over a chosen slice instead of the area, right? So we are going to do that, and we are going to have a corresponding detector that is aligned. In fact, we also talked about the different configuration, fan beam, cone beam. So for simplicity, what we will do, just to start on, we will start with like how it was first generation, where it was a pencil beam. So I had one line go through, I have one detector at the back, so it was a line. So we were collecting, right? So the X-ray was going through here, it was collected behind in the detector. So it was a line that was passing through. So we already know what is it that is getting detected at the detector. What is detected is the line integral. That is, you send something, and that integral, what is that integral? Oh, e power basic fundamental law, right? E power minus mu delta x, when we introduce that. Mu being the material property, delta x being the thickness of the material. So mu e power minus mu x, that is the fundamental law. Same thing we will rewrite. We will recognize what is falling on the detector ID is nothing but whatever you sent in, spectrum with different energies. Mu, the material property, is a function of both. S is your along the line segment. Okay, yes, we used I think x or r in our previous variables, but right. So S is just that same through, right, the line through, just a variable to denote that. So your mu is a function of along the line and energy. So this is the detector, this is what we know from before. Now what do we need to do? Okay, given this, we can quickly understand. In projection radiography, we didn't really bother in image formation. We understood this, whatever falls on the detector, we had intensifying screen, converted to optical density, we have an image of optical density that fundamentally was related to the underlying mu. But what you measured was this integral, you didn't really measure this ID got converted because of the photochemistry, right, the film, all those things, and you had an output optical density. Whereas our objective here in CT is, I want to somehow measure this mu along the S, right, along the path it came from. I am not just interested in the net sum. I want to actually go back and say, what is the mu along the path? How does the mu change along the path? Of course, there is another variable. Mu is also a function of energy. So, our objective in CT is going to be, we are not just happy about this ID. This ID should be simplified mathematically, right? This is good. It has to be, this expression has to be simplified so that it becomes mathematically tractable. Why? Because we want to use that mathematical tractable to our advantage so that we can end up getting this mu as a function of S, right, and E, okay. But again, like I said, it is technically a function of E, but in the instrumentation we also covered where does CT differ from your projection radiography with respect to all the other filtering and stuff. We are deliberately making it harden. Why? One of these reasons. What did we mean by hardening the beam? That is, you have a spectra of energy, you are shaving off, you are reducing the bandwidth. So the idea is, if I make it, I am trying to get to monoenergetic. I want to reduce the energy distribution. So I want to get through monoenergetic. That way, this variable is also a function of E. Then it becomes, right, two integrals. So what I can think of is, instead of using the two variables and two integrals, if I can use only one energy, so we introduce the concept of equivalent, right. It is like your center of mass, right, of the spectral. So we introduce this idea of E bar, the equivalent or the effective energy. So we can consider this as a monoenergetic model by using E bar instead of having this every energy. So we can reduce this to the first level by saying ID is I naught only this variable is there, this summation, this is monoenergetic, this E and dE, right, integral over E to E max of this, we are substituted that with only one energy, the average energy or the effective energy or the equivalent energy. It is all similar, it represents the same thing. So now you notice at least one level simplification we did, but we are still not done. We still have one integral here. Our objective is, so what you are detecting, this I naught is not a big deal. What is this I naught? Oh, intensity at the center of the detector when there is no object, right. That is how we use this I naught concept earlier. So essentially the I naught is you can get from calibration without even the object. Whatever you are sending into the object, what comes out at the detector, what you send through the detector, what you send at the front end of the body, ID is what comes out of the body. So the relationship between what you send and what you receive is, it is attenuated while it is going through the media with attenuation coefficient mu, right, that is what this is. So I can get my I naught. I naught is what you are sending. So without the object, if I have my detector, I can pick what you are sending into the body, right. So you can get your I naught. So essentially that means ID is something that you are going to measure, right, in the detector, whatever is going to fall on the detector. I naught is a calibration, so you can do that and you can have that upfront. What I don't know is I want this mu, which is the unknown. This d is not a big deal, right? I know what is my path. I know roughly the object size, so I can calculate d. That is not an issue. But I need to get this mu as a function of s, or the length, path length. So given a measurement of id and knowledge about I naught, we can rearrange this so that we have id by I naught minus natural logarithm. So this is a known quantity. So known quantity is your GD. So this is the GD is the measurement at the detector. But what is this measurement? What is this equal to? Oh, equal to this ln you take, exponential is gone. So what you have on the right hand side is just the 0 to d mu of this guy. So what this says is what you are detecting, right, what you are measuring at the detector, let me put it that way carefully, because what you are, remember the CT detector we covered, different from our previous one where it was converted to optical density. So this is what is measurement. It is falling on the detector and you are measuring it. So you have calibration factor. So you can measure, this is the quantity that you have measured, GD, right? This is an estimate. You can get GD. What is that capturing? That is an estimate of the line integral, right? So this is what you are measuring in the detector is nothing but it is a line integral of the attenuation values along the line 0 to d. Good. Kind of what we knew from before, we have just customized it. So what is our goal? Our goal is given GD, right? I have measured this, so I have GD. How do I say how it came from? What is the mu distribution? I am not interested just in the sum. I need to know at each location what is the contribution, what is the mu. Okay. So the idea is the basic measurement of CT scanner, right? The raw measurement. Raw measurement is a line integral. So from this raw measurement, which is a line integral, we need to construct the image. That's why the image is the object is already there. So we need to reconstruct the object. Object is already there, right? It's constructed, but we don't know. So we have measured the basic measurements in CT. Using this basic measurement, we need to reconstruct the object, the slice, right, that we want. That is the goal. Okay. So this is the basic measurement. So now we are going to see how we are going to get at it. Before we do that, we should appreciate, oh, this is a function of mu. Okay. But then if you go look at the values in mu for biological tissues, like you have a bone, muscle, fat, right, the difference between the mu is very small. So just by using projection radiography, right, if you got the projection radiography, this is a thing. If I can just, can I get to see the different tissues, the contrast out, right? The problem is in projection radiography we always calculated the sum, right? So there was enough contrast because the sum was greater than all the pieces. Now you want to construct one pixel along the line. So if the difference is small, which is inherently difference between bone and tissue is all small. So if you don't do anything and you just reconstruct this, your inherent contrast will be poor, meaning you won't be able to see much difference between, it will be too noisy. So what they do instead is, that is one thing. The other thing is, we talked about mu being material property. You already see here what you measure is also dependent on the system. right, the energy that you are going to use, how it is going to be calibrated, right, that system, what is going in, all of that influences your GD. So, if from GD if you are getting mu, naturally the initial condition of what the GD, right, what your I naught is, for example, is going to have an influence. What this equivalent energy, that is going to have an influence. So, material is same, that is ground truth, but the mu will change from machine to machine, right, that is a problem. Or even with the same machine, if I change my settings, mu will change. Or it is the same patient, I go to one scanner in one hospital location, I go to another patient, another scanner in another hospital location, or over time, right, any of this will give me different mu's, or at least there is a possibility to give different mu's. So, it is not just that okay we have GD and how can we get mu. If you get mu, the mu is influenced by all the other factors, and therefore, it may still not be as useful, okay. And therefore, what is done is we convert this mu into what we call as CT numbers, okay. So, if you look at your CT, if you had a chance to look at it and read the text and all those things, you would have seen the units, right. When CT, they call CT number, they also call in Hounsfield's units. So, what do they do? So, essentially what are the parameters, what are the tissues of interest to you? Inside the body you have air, hydrogen, water, and then various combinations, right, fat, tissue, muscle, bone, some density changes are there. So, the idea is I want to convert that. So, is there something that I can calibrate against, I can have a reference against? Usually water is taken as a reference, okay. So, these are the CT numbers are computed from attenuation coefficient at each pixel, that is you get some mu, but that mu is not sufficient because it can vary from scanner to scanner or settings to settings. So, we will have to convert that mu with reference to water. So, this we can do, we can have a test standard for water, right, under ideal temperature, you can have that. So, for that X-ray, before you do the human body, you calibrate it with water. So, you can actually get mu of water, you know. So, you can convert whatever mu you are getting with respect to water using this formulation. So, you are making the units 1000 times. So, you look at the, you are improving 3 orders of magnitude, so that you can separate out the different constituents, because inherently the mu between the different biological materials of interest is small, and therefore you kind of do this with reference to water. And what you quickly see is, if there is water, right, if there is water, if that location had water along the path, your mu will be mu water minus mu water, so that is going to be 0. So, your H, right, your CT number or the pixel value will be 0 if you have water. So, if you have no, what is the other, air for example, right. If you have air, air does not attenuate or insignificant, right, compared to mu water. So, essentially you can get, this can be ignored. So, you will get minus mu water by mu water. So, you can minus 1000. So, if it is air, there is attenuation is less than water. So, that how much less? So, it is pushed to minus 1000. So, the bone, which is naturally natural body, bone is supposed to have the highest attenuation of all the other material, right, fat, muscle, water, air. So, bone will become 1000 Hounsfield's unit, okay. So, H is 0 for water, minus 1000 for air, H for bone is about 1000 Hounsfield's unit. So, now you see your CT becomes quantitative, right? You have an image, CT image, each of the pixel has a unit which is Hounsfield unit. So what is the value going to range? It is going to range from -1000 to 1000. Usually within plus or minus 2 Hounsfield units you get accuracy. So it's pretty damn good, pretty damn good. Therefore you can actually start to do quantitative, right? So I can take the scanner, I can use Hounsfield unit as a parameter and say if this is greater, probably the material, so this is a tumor. So you can do quantitative, so you are not worried about which scanner center was taken. Okay, so this is very powerful. So let us appreciate this, and let's now go on to the real business. The real business is, if I get my mu, I know how to normalize, so I can get my CT number. So it doesn't matter on which scanner or what setting you used. Okay, so let us jump into the reconstruction itself. Okay, so just to reiterate, we are going to do parallel ray reconstruction. What is parallel ray reconstruction? We send one X-ray, I have one detector, one line integral, which is what we got. So we are going to mimic first generation, where then you translate, you send, receive, translate, send, receive. So you kind of have parallel lines. Of course in CT we talked about, we are going to move and take it at different angles, same thing, right? But in essence, if you look at our reconstruction, right, we are going to start with simple parallel ray reconstruction, pencil beam kind of word that we used in first generation. After we do this completely, then we can expand to fan beam and then expand to cone beam, what your slice, right, third direction, cone beam. So we can do all that, but this is something that is very fundamental and very powerful. If you understand this concept, rest of them is just going to be geometric manipulation on these algorithms. Okay. Well, let's start with this. First, setting the stage. So here is an object that needs to be imaged, or I would say this is the slice. This is the slice, right, that you need to image. You are standing on one side, so this is the slice. For example, you are going to send on one side, receive on the other side. I want to after that reconstruct this object through the slice. So this is what that is. So I am going to have f of x comma y is my spatial reference system. I have, this is the object in there. What do we get? We get a projection, which is what we saw. What is a projection? Oh, if I take an angle, right, line integral. So what you are getting here is a projection. So how are we going to call? In this case, what you are getting is a 2D is projected to get 1D, which is a line, correct? In our X-ray projection radiography, the object was 3D and we used cone. So 3D was collapsed to 2D plane of paper, whereas here I am sending only X-ray in a slice. So even though I am 3D, it is only this direction, this 2D imaging slice is what I want to image, right? So it's only 2D I want to image. So in this direction, right, when I collapse, this 2D becomes 1D. That is what you see. So what you are collecting, the data you are collecting is a 1D data. Along the length is the extent of this object, and the values are, oh, remember how we talked about, if you have one dimensional variable, you can plot it, right, with the y axis being the amplitude at each location. So this is your values at that location, which is nothing but, from what we covered so far in our context, this is nothing but line integrals. Whatever is sum total along the path is this value. Okay. So just to get our coordinate system and the representation of this correct mathematically, we will recall we wrote 2D line, right. So, we have to know this is your line which has a length L. So, that is one axis and it is oriented at some angle, that is theta. So, this line is nothing but L of L comma theta. What is this line? This line is nothing but a projection of this object f of x comma y, where this L, right, L is along the line. What is that? Oh, that is nothing but this L of this line along the line of sight, right. This is the one that is going to come. So, this is the distance, the perpendicular distance, right. So, that is your L, and theta is likewise where is this line making with respect to this f of x comma y, right. So, L can be defined in terms of where it is located, the small l, and theta, which is dependent on where this line of projection you are going to take, right. So, we are going to write all this out. So, L of L comma theta is nothing but in the xy plane where this constraint, right, x cos theta plus y sin theta equal to L, that is what is your L of L comma theta. So, now what we want to do? We want to go back to our projection. So, this is projection, right, that is what we want to do. So, g of L comma theta is nothing but f of xs comma ys ds. So, nothing but your projection is nothing but minus, so you are summation of f of xy is the object, you are summing along. So, x of s, y of s is this line, right. So, your g of L comma theta is nothing but sum along this line, that is this value. So, g of L comma theta, which is your projection, is nothing but sum of along the line segment. Okay. Clear. So, this is our line integral that we covered from this. What we need to do is, of course, you can calculate this x of s and y of s is this line. So, this is fine, this is your parametric form, but this kind of captures how we can write the line and how we can visualize the write down the parallel ray, how do you get projection in terms of the object and the line integral. But then there is another way we can write it, which is a more simpler form, right. That is, you should recognize what is this f of x y is your object here, the 2D object, but instead of writing it in this form, we can recognize that f of x comma y into delta along this line. That means you are picking from f of x comma y. Remember, we covered point delta and line delta. Why did we cover line delta? Oh, we said it will be easier if I want to pick a line from f of x comma y, I can define a delta function, the line delta function, and I can move the line delta function to pick values from wherever we want from f of x comma y. That is what we are doing here. So, we can also see this line as nothing but your f of x comma y, you are picking this line from f of x comma y. How am I picking this line? I just say the delta function exists only in this line, right. So, my delta function exists when argument is 0. Here, when is the argument 0? When L is equal to cos x cos theta plus y sin theta. That means your g of L comma theta is sum along x and y, right, of this f of x comma y taken along this line. Clear. So, this is another way of writing. So, for fixed theta, right, example here, one theta is what I have shown. This is called as the projection. Clear. You knew this from before, but we have just written it out mathematically. We talked about this line integral is nothing but the projection, right. You are collapsing the third dimension when we did projection radiography. Here you are collapsing the slice to one line. So, it is a projection. So, g of L comma theta is called as the projection, and this projection is at particular theta. Likewise, what can I do? Right? Likewise, what can I do? In the instrumentation, I will see it from different views, right? So, if I view it from different views, actually I can get a collection of g of L comma theta. Clear? So, this is for one theta that we showed here. If you move around and get the projection from different angles, then you have a bunch of g of L comma theta, bunch of projections, right? Each one is registered, you know which direction it is coming from, you know which detector, so you know your L. So, you have what is called as collection of projections. It kind of seemed intuitive, but what we didn't recognize is this collection is called as your 2D radon transform. So, if I give an object, if I reduce the dimensionality and I have reduced dimensionality or the projections from different views, right. So, for all L and theta, your g of L comma theta is called as the 2D radon transform. Okay. So, here at this point it begs the question, that means this is not something new. So, radon transform kind of all this work was published in 1915s, 20s like that, right. So, really early 20th century. When did CT come? Post World War II, right. They started working on that. So, you see, if there is a radon transform, you have projection, you could also imagine that there should be inverse radon transform, right. If you have forward radon transform, you have forward Fourier transform, you had inverse Fourier transform, you have forward 2D radon transform. So, you can also have, you probably can guess, there should be some inverse 2D radon transform. If there is inverse 2D radon transform, given the projection you can get, given this, you can get the object, which is what you want. So, the thing is, mathematically it grew, but we are very lucky, we can turn back and we have hindsight, it's all 2020, right. So, we can turn back and say, oh, this is actually common sense driven way of doing it, right. So, given this, I know how to get the image of the f of x comma y given the collection in a very intuitive way, which is what I will attempt to do, and then of course put it mathematically so that it is correct. But it is not that easy. I mean, the reason I want to do it that way is, maybe if you have an appreciation for this, what is not so obvious now, maybe you may start to see something that is not obvious, and you may push the understanding further. Okay, so just for that reason I am kind of trivializing and saying, oh, this is common sense, but nothing is easy. So, what we will do is, let us relate right now what we have, projection and radon transform, right, we just completed that. So, let us just put that, because we just said f of x comma y, g of L comma theta, we will just quickly formalize this. That was parallel development by radon. Let us now see why that radon transform, that idea is applicable to the values that we do, or the CT problem proposition. So, f of x comma y is your mu of x comma y, right. You can see that in our context we have mu of x comma y, which is similar to the f of x comma y that was shown. G of L comma theta, the projection is this measurement, right. So, f is the underlying unknown distribution, in our case it is going to be mu. G is the collection of projections from different angles. So, now you see the big picture. Our objective is, how do I get mu from G, correct. So, let us take a simple example just to get this comfort. Consider an image slice which contains a single square in the center. What is a projection? So what I would like for you to do is, when you get time, when you have time to scribble, start to imagine. So I actually said at the beginning of this module, right, CT module, I had a Rubik's cube and I told you start to imagine. So keep doing that, but given that we are here, let's do a simple object. At least that will make my life easy, right? But you should take complicated objects and try out what we are doing here. So all I am saying is, consider an image slice which contains a single square at the center, right? I am trying to make that colored so that you can see that this is there is a target inside the field of view. Okay, this is the slice. So our objective is, I don't know this. This is the ground truth, right? I want to image from outside and try to see if I can come up with something that is close to this, right? So first step towards that is whatever we covered. What are we measuring in CT? It is projection. So can you draw the projections at, say, for example, 0 degrees. So, right. So I am going to have my L, comma theta. Theta is 0 in this case because I am taking a simple. So what is this value? What is this going to be? This is going to be my G of L comma 0, for example. What is this going to be? Oh, brute force interpretation. It is line sum of, right? So minus, so this is my length. So if I take this to be 0, minus L by 2 to plus L by 2, or whatever length you want to give this, right? Let's A by 2 minus A by 2 to A by 2, A being the width. You see what's happened? Oh, what is my projection? 0, 0, 0, 0. Right? 0, 0. So line integral, all this is 0. So I have 0. When I come to this location, now I am going through the square. So that means it is going to sum along the square. So that means I have to have a value that goes up, and that remains same because rest of the parallel lines, right, when we go through the L is same. And then how do I get out of this? Okay, and then it comes down because after you cross, so I am just trying to sum along the lines, right? That is what your interpretation is. Again it becomes 0. So this is some value which is the sum integration of this length, right? So if I had one value of 1 inside the box and 1 per unit length, right, each value, and I have a length of, this is A, right, square I said. So this is, let me just, I've used A, so this is B, so this is B, right. So if it's 1 unit per length is the value, then if I go through B, I will have B, right, because I get sum of that. So I have B, so I have 0 and then it raises to B, and then it is always B inside the box because the length is not changing and all of them are having the same value. And then once the line comes outside this box, I get 0. This is one simple projection. Clear? So likewise you can do, say for example, 45 degrees. These are the careful, you have to be careful how you want to do it. Again, just for convenience, I am going to draw the amplitude the other side, okay. So here what is going to happen is going to be 0, I am going to have some non-zero value starting here until here. So, it is going to be 0. Once I come here, it starts to raise, right, and diagonal will be my maximum path length. So, I am viewing from here, right. So, my lines are going to be parallel like this. Sum of lines is going to be 0, start to increase, start to decrease, 0. Clear? Likewise, you can go about do. So, this is the bunch of projections you have. I want to get to this object, but what I have is, I have these collection of these projections. I have one projection, I have two projections. Likewise, you can do it for the others as well. Clear? So, I have bunch of projections. So, what we will do is, okay, given that you have bunch of projections, how do we get back to the object? That is what we will see. Again, these are some things that I kind of tell that you do it by yourself, because I have shown you for square, simple, do it for rectangle at your own time. Okay, what you will realize is the carefulness with respect to your length and how do you, what is your path length and therefore your shape that you are going to see here. You will get familiar with that, that is why. Okay. Because most of the time this is something that you can do by paper and pencil, but a real object you may not be able to do that, you may want a computer program to do it. Anyway, so now first, before we go further, I have this bunch of projections at different angles. What do I do with them? Yes, you have to use them to get to the image, that much is clear. But before that, is there a way that I can organize myself? Can I organize the data that we have collected in some form, so that at least we can see some information from that before we actually do brute force reconstruction? Okay. So, nothing, what you have, we get what is called as a sinogram. What is a sinogram? It is a raw data, the data that before any other processing and reconstruction, it is the data that you have collected, which is the line integrals. So, it is nothing but an image of g of L comma theta in rectangular coordinates. So, rectangular coordinates means you have to have two axes. So, one will be your L, the other will be your theta. Okay. So, it is a pictorial representation. So, this is your pictorial representation of your Radan transform of f of x comma y. So, this is the data that we have collected, this is the raw data. So, if you just plot that, so this is the object f of x comma y. If you were to project this, right, you will get one projection, like how we did for square just now. If you project this, right, when you do the sum, you will get some value. So, that will be one projection. So, when you go to another angle you project, you get another projection. So, if you stack all this, so this will be your L and you stack different thetas. So, your y axis is your theta axis. This representation of the data that you have gathered is called as sinogram. Why is it a sinogram? Well, I think the quality of the figure is pretty reasonable. I hope it comes through like that, where you can probably appreciate, right, there is some curves that you see. In fact, if you tilt this, right, rotate it 90 degrees, you will be able to see that the curls are nothing but it looks like a sinusoid, right here. You have some sinusoids. Now it is vertical. So, if you actually rotate it, you will see that it is the typical sinusoid that we are used to plotting. And so, the name derives because you see these sinusoids. It is a fundamental, if you have a point, it turns out to be a sinusoidal feature, and therefore, this is called as a sinogram. Okay. So, that is for the name. And then what else do you see? I mean, this is important. What else do you see? Oh, I do see that there is a hourglass shape, something is there. But if you interpret what is the meaning of each of the projections, right, then maybe we can glean one more information, which is oh, if I project from 0 degree, for example, this object looks to be the fattest, right? It is more wide than tall. So, if I project from here, my length will be more. Oh, so this is 0 degree, for example. So, your 0, you have L is more, and then as you move around in small steps, the length decreases, and when you get perpendicular, right, at 90 degrees, this is the projection you are getting this width now, which is smaller than this width. So, gradually you go, you get to 90 degrees, you get the shorter width, and then again when you start to move away, so you stop just before 180 degrees. Why? Because you then 180 degree you are starting to see the same pattern, right? You project from this side and collect on the other side, or project from this side and collect on the other side, it's the same line. So, the line integral is going to be the same. And so, typically this sinogram plot is having L and theta, and the theta usually is just less than your pi, and you have several of them depending on how is your stepping size, how many different views you are stepping, that is going to determine this axis. How many detectors you are going to have, or how many parallel in the if you think about it as translation, or you think about an array detector, how many array elements are there, that is going to determine your axis here, right? How many points you are going to have along this axis. So, you see that sinogram is having some information. From this you can actually measure the size of the object, width of the object, and so we can get that. However, it does not, and also you see there are some bright spots, dark spots, right, cancellations. Where is that coming from? Oh, if it is bright, that means it so happens at that angle some of these whites align themselves so that it is high. When it is dark, maybe it is cancelling, right. So, you could actually interpret this image, the sinogram as well. There are some information, all the information is hidden though, right. So, even though it has all the details, like the underlying information of the object is there, clearly if I tell you that okay, this has all the information about the object, so you can start to see the object from sinogram, is impractical. It does not make, I mean, for sake of argument we can say, oh, we can get the length and breadth of the field. So, I know the object dimension, so we got some information, but this is no substitute to actually visualizing the object. Okay. So, sinogram is the raw data, it is organized in a form, but essentially even though it has the information, it contains the information that we may need, it is in a form that is not appreciable from an imaging perspective, as an image perspective. Okay, so what we will do is, how do we start with the sinogram and hopefully get to this image or estimate of this image. So, this is the ground truth. These are the estimates of projections. So, using these measurements, how do we construct or reconstruct or get an estimate of this image of this object? That is what we want to see. Okay. So, here this is what I will do. Quickly, conceptually, I will just tell you what you and I would do, right, if we have a problem. It is an analogous problem. I am saying that, imagine same square example, right, just for the sake of simplicity I am just putting some matrix, so that you can start to maybe get the big picture of where we are heading to. So, now I am saying I am not even worried about X-ray CT. My problem is this. See, I have 1000 gold coins, right, and what I want to do is, I have people standing in rows and columns, right? I have people standing in rows and columns. I have 1000 gold coins. So what I do is, I stand here to the first person and I say, here, bunch of 1000 gold coins. You take one or take two and pass it along back, right? So that each one takes, and I come to the other side and I take the remaining. So my problem is, I have so many people and initially I say all of them are good, I want all of them to take only 2, okay. But I do this experiment, so I give this 1000, all of them are taking 2 or supposedly instructed to take 2 or whatever and pass the remaining. Next I give the 1000 coins to the next row, next column, right, do the same thing. So I have done that. Now the problem proposition is this, I have only this, I know what I sent, I know what I received, so I know what is lost along the path. If all of them were honest, then no issues, right? But it turns out that few of them somewhere, say let us say just for the simplicity of argument, there are about 4 or 5, 6 whatever number of people there. In fact, it can be anywhere. Just for simplicity, I am just putting at the center. I am saying, well, these people, they are not, they are dishonest. They are taking more coins. So now my problem is, how do I find out who these people are? Where are they standing? If I know where they are standing, I can pick them up. But I don't have any other information. All I have is, I send here, I ask them to take 2 and all of them are same number of people are there. Whereas when I sent 1000 here, I got some 1000 minus, say if there are 500 people and I asked them to take 1 each. I sent 1000, I got 500 back. Okay. Whereas when it comes here, I got only 400. Here I have 500 or more or less, right, plus or minus. So the problem is, at a first guess, what I can do is, I could say, well, I sent 1000 and roughly there are so many people there and I asked them to take 2 each, and so I would have expected this back. But along this column, something came low. But that is not sufficient for me. See, you cannot accuse somebody without knowing who it is, right? I may guess, maybe there is something fishy happening, but may not be. Even here, maybe there is someone here who is taking more and there is someone else who didn't take, he just passed on. So on an average, you would have got the same number. So it does not really matter. So the point is, how do I suspect? So without having more information, I cannot do much with it. All I know is there is a problem. What would you do? Well, what if you have the luxury to do, what you should do is, I have a suspicion. So let me do this. Now I will start to send 1000 coins and I will say, you start to send not to the person just behind, but at this angle, right? Right. Then I will go, I will send from here and ask them to pass to their side, right. This is nothing but similar to your projections, correct. It is very similar to your projections. Now how will I do? What will I do? My first guess would be, how would I start to approach to nail down who could be the guy? Oh, my first approach would be, look, I sent 1000, I got 500. I pretend everybody is nice. So what I am going to say is, from this projection, right, I got this value. So I sent 1000, I got 500. So let us say, but when you go here, there was a dip, right. This is the data I have. So I have done this. So when I do this side, similarly I get some value, dip, right. These are my projections from different views. What will I do? I will say, look, I don't care, I will be honest, I lost 500, I will say I gave everybody 500 I lost, divided by, say, if there are 500 people, I will say everybody took 1. So based on this data, I will say along this column everybody took 1 rupee, 1 gold coin, 1 gold coin, 1 gold coin. When I come here, I will say, oh, I know it is only 400, there are 500 of you. So in this column, for lack of much detail, I will say 600 by 500, 1.2. Each of you are supposed to take 1. In the other cases, they took 1. Here, each of you have taken 1.2. I can say that because I don't know, I trust equally likely. So I put 1.2. And I repeat the same process. I will say, okay, based on that, that is what I did. When I stand here, I will start to do the same projection. Right? What is that? From projection, I am giving it back. So it is back projection. So from the collected, right, from the net sum, I am projecting along the, I am back projecting it back and saying each of you probably got this much. So it turns out that that is not a bad idea, right? It's a common sense thing. So if I can collect like that, I will start to project back. What will happen? Let's formalize one more step and then we will see how nicely this identifies or makes us help identify the culprits. So it is a simple approach. We assign the projection values at g of L comma theta naught back to all pixels along the lines, right? This is what I did, back to all pixel along the lines. I have given that. The resulting image is called as back projection image. So we will write it mathematically, back projection at theta from one theta value of x comma y is nothing but the same projection that you have g of g, right? You are projecting for that theta along that line, x cos theta plus y sin theta comma theta. So you have projected that back along. So I had one line, right? I had one projection. I have back projected that to this f x comma y space. Clear? So we'll just take a pause after this slide because we'll have to have the energy to do the reconstruction. So if you take one example back projection from the object that we showed in the previous slide, right, it will be like this. Nothing fancy. Here I took a square just to explain, right? If you project this back, what is going to happen? If I project this back, what is going to happen? Just for getting an analogy, if I back project one thing, I am just saying all of them had 1.2, rest of it is, whereas the other values, if we go by our analogy here, the others were 1, right? This is 1, this is 1.2 in the example, 0.8 coin, this is 1 coin and an average per person. So I am saying everybody took this. So here I am back projecting. So I am saying along this column everybody took 1.2. Along the rest of the columns they all took 1. This is my back projection image at 0. At 0 of x comma y. I mean this is back projection of the 0 angle, view angle along x comma y. So one dimension becomes 2 dimension, right? Likewise, the complex object that we saw in the previous slide, if you take an example 30 degree sinogram, if you take the one at 30 degree and project it back at that angle in that space of x comma y, this is the object. Okay. So let us stop here. Let us continue further and see the beauty of how from this baby step, how we can actually get the reconstructed image. Okay. Thank you.